Okay, welcome back. We're going to continue with the level 3 electrotechnical technology, and here we have outcome 6, again continuing with outcome 6, session 8 and 9. Now we're going to be looking at single phase induction motors. Okay. Okay. And outcome 6, understand the functions of electrical machines. Okay, let's just go into that, make sure you can see it. Okay. Now the student will be able to understand, or as well as should be able to understand, identify single-phase induction motors and distinguish between series wound, slip-phase capacitor and capacitor-start run. Okay. Identify single-phase induction motors and distinguish between series wound, slip-phase capacitor and capacitor-start run motors. Okay. And this again is our normal session, just simply reviewing what we've done before. Okay, now read this for yourselves. Okay, make sure you can read it through and that it reflects as to what we have done previously. Okay. Single-phase AC machines. Now, in a three-phase machine, it is the interaction between the rotating magnetic field and the magnetic field created in the rotor. In the rotor that causes the rotor to turn, making it self-starting. Okay. Okay. Now, in a single-phase AC induction motor, there is no rotating magnetic field, so it is impossible for it to self-start. Three-phase machines have three magnetic fields, rising and falling. The single phase only has one, so a false rotating magnetic field needs to be created. And this is how we're going to create that false magnetic field, to give the impression that it is a rotating magnetic field. The single phase supply creates a pulsating magnetic field rather than a rotating one. A second magnetic field needs to be created by the supply to get rotation to occur. There are three types of single-phase induction motor, each having a different way of creating the second magnetic field. Single-phase split-phase induction motor, single-phase capacitor-start induction motor, single-phase shaded pole induction motor. Okay, let's just make sure that you can see this for yourselves and that I just want to make sure that you can see the information and that remove any glare, hopefully, that might be on it. So let me just pan down a little bit, make sure we can get it all into frame. Okay. Okay, let's just rise again. Okay. Now pan back so we get the frame fully in frame. Okay. Now just moving a little bit more. Okay. Now again, you need to extract this information. You need to write it out. You need to create your own notes from the information, and you need to do additional research as well. Now, single phase, split phase induction motor, and here we have, okay, and again you would see something like this already in one or two of the videos I've done, but remember, it is always a continuation of what you have been shown before. Again, here we have U and U1, the ends of the coils. This is your run winding. Okay, here you have your start winding. Now this winding only comes into play at the initial start of the motor itself to get the motor going. But once the motor is going, the centrifugal switch is then open, and that isolates the start winding, and then the motor is then running by its own inertia against the magnetic field set up in the run winding. Okay, now again draw these out. Okay, now I'm just gonna make sure I can get all into frame. Okay, 1 second, bear with me. Okay, we have a main run winding, that is the winding that is used when the motor is running. This is a large coil of wire which, when current flows through it, creates a pulsating magnetic field. We also have a second winding which is connected in parallel with the run winding. Okay. The length of the two windings are different, which makes the magnetic fields rise and fall at different times. So for instance, in this case here, we may have a winding with 10 turns on it. Then we may have the start winding with 5 turns on it, okay, etc. And that's the difference within the two windings. The variation in the two magnetic fields is sufficient for the motor to self-start. Okay. Okay, thank you. Right, here we have now a 1 horsepower induction motor. And here's your start winding and your run winding. Okay, that's a resistor in series with your run winding. Okay, and you also have a resistor in series with the start winding. Okay, what these two resistors do, they tend to create what a phase shift. So what happens here is that you get a lagging effect. So although one supply is at one angle, by changing your coil, adding a coil, you've caused a phase shift. So you got one supply running as normal, then you got this lagging the supply. Okay. So your start would be here, okay, would be lagging your supply voltage by so many degrees. Your run will then also be lagging your supply voltage by so many degrees. It is this lagging voltage that causes a cycle, a inductive cycle, that causes the motor to rotate. Okay. So here, yes, start angle, run angle. Okay. Now, by having these angles, this angle here, your start angle, lagging the supply voltage, you cause what's called a phase shift, and that will cause to give the impression that the motor is actually rotating in a magnetic field. Okay. And here you then have, once you've started and you drop your switch back to run, you're then having it's lagging even further, and that gives you your rotating magnetic field by having this angle lagging your supply voltage. Okay. Now, the length and therefore the resistance of the windings are different. This difference in resistance and inductance creates a difference in impedance, and so we get a different phase angle between the run and start windings. Simply by putting in a resistor, we have caused a phase angle to occur. Okay? And by changing the size of our windings, we created a different angle also, even more so. Okay? This difference means that the magnetic fields that they produce will be rising and falling at different times, and that will generate the cycle for your motor to rotate. Okay. Now, here we have a split phase induction motor connection diagram. Now, look at the diagram. Run windings, start winding. Okay? And again, here you have your what I refer to as switch, your centrifugal switch. Okay. Okay. Now, the variation in the two magnetic fields is sufficient for the motor to self-start. At certain speeds, the centrifugal switch opens and the start winding is open circuited. This type of motor has a good starting torque, usually 1.5 times the full load. To reverse the direction of the motor, reverse the start windings or the run winding connections, and you will see that these connections here can be interchanged. Okay, and that will change the direction of your motor. Okay, thank you. I'm just going to look up now a bit and pan out. Okay. Again, you should be drawing out these diagrams. Okay. Single phase capacitor start induction motor. Okay. And here's where we are single phase capacitor start induction motor. Okay, again here, this is your capacitor, start winding, run windings, okay, your centrifugal switch, your rotor. Okay. And you should know by now what this is and how this works. Okay, screw case criteria. Right now, the only real difference between this and a split phase motor is the addition of a capacitor, which improves the starting ability. The capacitor start and capacitor run has a capacitor that switches in via the centrifugal switch when the motor has reached a certain speed. But when you put the start handle up, what happens is that centrifugal switch is connected, okay, and that will run for a certain time. That causes a phase shift. The capacitor then connects into the circuit. What happens is the capacitor connecting causes a phase shift of the supply voltage, and that allows you to begin your motor to start rotating. Okay. At a certain speed, the centrifugal switch will drop out, and therefore dropping out your capacitor. Okay. Okay. Capacitor start induction run motor. Okay. And here now, I'm not going to read this out to you now. Okay, so you can begin to look at this for yourself and read this for your own self. And again, look at the phasor angle. Okay, these are called phasor diagrams. Okay. And remember, this here will represent 180 degrees. Okay. And again here you have your capacitor start motor. And again here you have your capacitor in series with your resistor. Your start winding, right? Your start winding creates a kind of an inductance in regards to these components, okay? Okay, I'm just making sure it's in frame. I don't need to do a lot of talking now. Okay, this is for you now to read and to do your own additional research. Now draw out the diagrams. Okay. And here you have connection diagram for a capacitor start motor. Okay. Capacitor, centrifugal switch. Okay, single phase supply. Okay. Let's just make sure you can see it and I can get a good picture of it. Okay. Draw them out, make them your own. Okay. And these are just various types of single phase motors. Okay, shaded pole induction motor, This is the simplest single-phase AC motors, okay? Shading ring limits eddy currents, okay? It reduces eddy currents, okay? When you're dealing with motors, motors tend to create eddy currents, and you need to reduce that because eddy currents creates heat, and you do not want a lot of heat when you're running a motor. Okay, let me just go back up and make sure we can get it back into frame. Okay. 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 Shading rings, okay. And again here, cage rotor, etc. rotor, magnetic core, okay. Shading rings are solid pieces of copper, and these are your shading rings, okay. Shading rings are solid pieces of copper looped around part of the core. These have low resistance and a large area. They create a different path for the magnetic flux, and so two effective magnetic paths are created. These paths are sufficiently out of phase with each other and link with a rotor, enabling it to turn. This type of motor has poor efficiency and a low power factor. However, it is also very quiet. They are often used as fans for cooling power supplies. Okay. Okay. I hope you find this useful, okay? And again, remember to read the information, write it out, make the information your own, okay? And make notes, make notes, make notes. And don't forget, safety, safety, safety every time, okay? All right, thank you. I hope you find it useful. Bye-bye for now. Thank you.